think we'll all survive.
So we're going to take a break from circuits for a little bit and talk about aircraft batteries. Today we're going to cover lead acid batteries, and I'm hoping that on Wednesday we'll cover NiCad batteries and the charging of batteries, and hopefully finish up batteries this week. So starting with lead acid batteries, today we'll talk about what an anode, cathode, and electrode is. We'll talk about primary cell and secondary cell batteries, battery ratings, the life cycle of a battery and what affects the life cycle. We'll also talk about the construction of a lead acid battery, and then lead acid battery testing methods and charging methods we will get into hopefully in the second part of lecture on Wednesday, depending on how far we get through today. So electrodes. What are electrodes? What's an electrode? In simple terms, an electrode is a conductor that helps in establishing electrical contact with a non-metallic part of a circuit. Electrodes consist of two main points known as cathode and anode, which basically describe the direction of flow of current. Anode and cathode. Both are defined by the flow of current. A cathode is an electrode from which the current exits a polarized electrical device. And an anode is an electrode from which a current enters into a polarized electrical device. What is the charge of an anode and a cathode? The anode is regarded as negative in a galvanic or voltaic cell, and the cathode is deemed positive. The anode is the origin of electrons, and the cathode is where the electrons flow. Here, this is a table of differences between an anode and a cathode, what their definition is and what the difference is between them. So, like we just talked about in the last couple of slides, the anode is the electrode where electricity moves into, and the cathode is the electrode where electricity is given out or flows out of. The anode is usually the positive side, cathode usually the negative side. Anode acts as an electron donor. Cathode acts as an electron acceptor. An anode in an electrolytic cell, oxidation reaction takes place at the anode. And in an electrolytic cell, a reduction reaction takes place at the cathode. In a galvanic cell, an anode can become a cathode, and in a galvanic cell, a cathode can become an anode. Primary cell batteries. The primary cell battery is like our common household battery. Battery we use in our TV remotes, clocks, other small devices. We have a diagram here of a primary battery and how it is made up. Negative and positive terminals. The canister is made of zinc. You have a gasket there. The zinc is consumed, and we have an electrolyte paste, a carbon rod, and cathode mix. The zinc canister acts as the anode, and a carbon rod acts as the cathode. The reactants in these batteries are consumed after a certain period of time, rendering them dead and cannot be recharged. A primary cell battery cannot be used once the chemicals inside it are exhausted. So primary cell batteries, once they're used, they're totally dead. As we know from, if our remote dies, we have to change the batteries. We can't reuse those batteries. We can't recharge them. The common household, like Duracell type battery. Another type of primary cell battery is the mercury cell. The mercury cell is a zinc-mercury amalgam. It's used as an anode, and carbon is used as a cathode. A paste of mercury oxide, HgO, is used as an electrolyte in the mercury cell battery. These cells are used only in devices that require a relatively low supply of electric current, such as hearing aids and watches. We also have our secondary cell battery. Now, these secondary cell batteries can be recharged after use by passing current through the electrodes in the opposite direction, from the negative terminal to the positive terminal. A lead storage battery that is used in automobiles and inverters can be recharged a limited number of times. The lead storage battery consists of a lead anode, and the cathode is a lead grid packed with lead dioxide. Sulfuric acid with a concentration of 38% is used as the electrolyte. And another diagram of your secondary cell type battery. In order to recharge a secondary cell battery, the charge is transferred in the opposite direction and the reaction is reversed, thus converting lead sulfate back to lead and lead dioxide. Another example of the secondary cell is the nickel-cadmium battery, NiCad. These cells have high storage capacities and their lifespan is relatively long compared to other secondary cells, but they are difficult to manufacture and maintain. Construction of a lead acid battery. The battery is several cells connected in series, parallel, or combination. Aircraft batteries have all cells connected in series. Lead acid batteries have low energy to weight ratio and low energy to volume ratio, which makes them very heavy and large. But they do have good ability to deliver high current for a short period of time. This makes lead acid batteries ideal for aircraft engine starting. Internal combustion engines need a short burst of high current in order to start the engine. So that's why lead acid batteries are good batteries for internal combustion engines. Here's just a diagram of our common aircraft battery installed on a Cessna 152. You see right here, we have all of our cells connected in series. So this is a 2, 4, 6, 8, 10, 12. And I've put a couple of diagrams up here for you guys to see the cutaway of how a lead acid battery is constructed. In this diagram, we have a lead acid battery that contains 6 cells at 2 volts each. Each cell is rated at 2 volts. Here it's showing you the cathode, this pink area. Linked plates with grids filled with lead oxide, PbO2. We have our plate separators. And the anode, this greenish color, linked plates with grids filled with spongy lead. We also have another diagram. This points out the electrolyte acid. The acid in a lead acid battery is a water and sulfuric acid mix. When the battery is fully charged, it's about 30% sulfuric acid and 70% water. And we have our cells here that have our lead oxide, and a separator. Another good diagram just shows you the breakdown of the entire battery. Our terminals, relief valve for our acid, The electrolyte is pointing to where the electrolyte is filled in this container, and then the plates are placed inside. Construction of a lead-acid battery. Most light aircraft operate on 12-volt or 24-volt electrical systems. The lead-acid batteries that are used in these systems are built up from cells. Each cell outputting 2 volts and connected in series provides the desired voltage. So each cell actually puts out a little more than 2 volts, but according to aircraft battery ratings, it's rated at 2 volts per cell. They actually tend to put out 2.1 or 2.2 volts, and we'll talk about that here in a few upcoming slides. Lead-acid battery facts. These are a lot of facts about lead-acid batteries. Good to know. Definitely will want to know for the quiz and testing purposes. So the positive plates from the lead-acid battery are made of lead peroxide. Negative plates made of spongy lead. The electrolyte fluid, as I mentioned, is a 30% sulfuric acid and 70% water mix. This is when the battery is in a fully charged state. To neutralize the electrolyte acid, if there is spilling or if you need to neutralize that acid at some point, you can use baking soda. Specific gravity of a lead-acid battery should be 1.1 to 1.3 times as heavy as pure water. That's the specific gravity for your electrolyte fluid. We will talk more about specific gravity. OCV stands for open circuit voltage. So the open circuit voltage of each battery cell is about 2.1 volts. It can range from 2.1 to 2.2. The only time that you will need to know that is if you are calculating internal resistance, and the specific cell open source voltage will be given to you. In a lead-acid battery, the chemical process takes place during discharge. The lead sulfate builds on plates during discharge. Sulfate has a very high resistance to current flow. So as that sulfate builds up, creates a high resistance to current flow, and I'm sure that many of us have seen that white powdery film that comes on a really old battery, and that's sulfate. And that sulfate creates a resistance to current flow, which makes it harder for your battery to work properly. Electrolyte changes to water during discharge. There is a higher freezing point temperature for discharged batteries compared to charged. There's a lower freezing point temperature for charged batteries. The higher concentration of acid raises the specific gravity of the electrolyte and lowers the freezing point. So in a fully charged battery, we have a higher concentration of that electrolyte acid, which raises the specific gravity, and that's what creates a lower freezing point. Hydrometer testing. So we can use a hydrometer to test the cells, to test the electrolyte fluid. And we will talk more about hydrometer testing when on Wednesday when we talk about charging and testing of batteries. But in a hydrometer test, you want to take the test before adding water to your discharged cells. When your cells discharge, that chemical reaction is going to happen, and eventually when it discharges everything, it's that electrolyte fluid turns to water. In order to maintain specific gravity and to keep your battery working correctly, there are times where you're going to have to add water to the cells in order for for the battery to continue to maintain its performance. In a hydrometer test, there is no temperature correction necessary between 70 and 90 degrees Fahrenheit when using the hydrometer. But below 70 and above 90, you do have to make a correction for temperature. And that calculation we'll get into as well when we talk about battery testing and charging. Battery load testers. Battery load testers calculate using open current voltage and closed current voltage and current load. There are vent caps on lead acid batteries, and these contain a lead valve designed to close the vent if the battery is inverted, so to avoid spillage of the electrolytic fluid. Gassing occurs during entire charging operation, so a well-ventilated area is necessary. So specific gravity readings. We can read specific gravity with a special tool. And a specific gravity reading between 1.3 and 1.275 indicates a high state of charge. A specific gravity reading of 1.275 between 1.275 and 1.240 is considered a medium state of charge. And between 1.24 and 1.2 is considered a low state of charge. Aircraft batteries are generally considered small capacity but are subject to heavy loads, so the values required for the proper state of charge are relatively high. In talking about battery ratings, the voltage of a battery is determined by the number of cells connected in series from the battery. It's a typo there. Form of the battery. Whoops. Battery voltage is determined by the number of cells connected in series to form the battery. Actually, that was correct the first time. Hang on, let me correct this here. If I don't correct it now, I'll forget. Where'd it go? Here it is. So the voltage of one lead acid cell is rated at 2 volts, as I talked about before, but it actually, what the actual voltage is it's usually 2.1 or 2.2 volts, somewhere around there, so just above 2 volts. A 12-volt battery, therefore, has 6 cells connected in series and rated at 2 volts per cell. So 6 cells rated at 2 volts gives us our 12-volt battery. Amp hour rating. Amp hour rating measures a battery's storage capacity. It is determined by multiplying current flow in amps by the time in hours that the battery is being discharged. So as an example, we have a battery with a 1 amp hour rating. It will supply a current flow of 1 amp to a load for 1 continuous hour. Or, in the same way, it will supply a current flow of 2 amps for 1/2 hour. It could also supply 3 amps for 1/3 hour. So any of those combinations would be the supply. A battery of that rating would be able to supply that type of current for that amount of time. Any of those combinations. Amp hour output will depend on the rate at which a battery is being discharged. So at the rate which the battery is being used. Increased heavy current being discharged will increase heat in the battery and decrease the efficiency of the battery. Aircraft batteries have established a standard 5-hour discharge time. That doesn't mean that all aircraft batteries will last 5 hours. That just means that's how they're rated. This is only a basis for rating and does not necessarily mean the length of time during which the battery is expected to furnish current. Under actual service conditions, the battery can be completely discharged within a few minutes, or it may never be discharged if the generator provides sufficient charge. Amp hour rating is determined at a 5-hour rate unless otherwise noted in regards to aircraft batteries. So as an example of that 5-hour rating, if we are using if we have a battery that is able to supply 40 amp hours, we could use 8 amps for 5 hours. So that's our 5-hour rating in aircraft, okay? Amp hour capacity is dependent on total effective plate area in a lead-acid battery. Connecting batteries in parallel increases amp hour capacity. Connecting batteries in series increases total voltage, but not amp hour capacity. Okay, so this is different than we said the cells of aircraft batteries are connected in series, but here we're talking about if we're connecting batteries themselves in series or parallel. So thinking of if we want to take one battery and connect it to another, if we connect it in series, it will increase total voltage but not amp hour rating. If we connect one battery to another but in parallel, it will increase amp hour capacity. Small batteries are rated in milliamperes, large batteries rated in ampere hours. Our aircraft batteries, lead-acid batteries, have a standard 5-hour rating and are rated in amp hours. Some battery terms, these are going to be used in your FAA testing questions you'll see for some mathematic equations. So OCV, or no load voltage, CCV is closed circuit voltage, CCC is our closed current, closed circuit current, and internal resistance, and OCV is open circuit voltage. Open circuit voltage, OCV, also called no load voltage. This is measured across terminals. As an example, open circuit voltage of a fully charged 12-cell lead-acid battery is approximately 26.4 volts. That means we have 12 cells at 2.2 volts, and multiplying those would give us 26.4 volts. That would be your open circuit voltage. Circuit voltage, also called loaded voltage, is measured across terminals. Voltage of battery when load is applied. This is also the same as voltage drop across the load. And your current times resistance of the load is going to give you your internal resistance. So this is what we're going to use closed circuit voltage to calculate. Closed circuit current. This is the current being furnished from the battery when a load is applied. Internal resistance. Batteries have internal resistance. So this is the resistance inside the battery that restricts current movement. It becomes greater as battery becomes discharged due to lowered CCL. And formula for determining battery internal resistance is as follows. We have internal resistance equals OCV minus CCV divided by the load in amps. Calculating internal resistance. So here I have an example. If we have a 6-cell battery connected in series, which all of our cells are connected in series in aircraft batteries, the no load voltage is 2.1 volts per cell. If this 6-volt battery furnishes 6 amps to a load of 2 ohm resistance, how would you calculate the internal resistance of the battery? So our formula for internal resistance, our open circuit voltage minus our closed circuit voltage divided by our closed circuit current. Our open circuit current, whoops, that's supposed to say open circuit voltage. This is our open circuit voltage based on our equation in the previous slide. So we have our open circuit voltage is the 6 cells at 2.1 volts each. So you're going to take those 6 cells and multiply the voltage rating of the cells to get your open circuit voltage. And that's going to give us 12.6 volts. So our open circuit voltage from our problem here, our 6-cell battery connected in series, and I'm telling you in this problem that the no load voltage of the cells is 2.1 volts. This makes our open circuit voltage 12.6 because we're going to take the cells and multiply the voltage rating of the cells by how many there are. Our closed circuit voltage. And remember, we're doing all of this because we're plugging it into our formula. So we have our open circuit voltage. What's our closed circuit voltage? Well, our closed circuit voltage is the current times the resistance, and it's basically just our voltage drop. So we said in the problem, this 6-cell battery connected in series, and I gave you the no load voltage of the cells. We calculated the open circuit voltage. So this battery furnishes 6 amps to a load of 2 ohms resistance. So this is our voltage drop, or our closed circuit voltage. 6 amps times our resistance, 2 ohms. So our closed circuit voltage is going to be 12 volts. What's our closed circuit current? Well, we said in the information in the problem that the battery is furnishing 6 amps. So those 6 amps, that's our closed circuit current, because that is the current being delivered to the load. We have our formula. We're trying to find internal resistance. So internal resistance equals open circuit volt. Yeah, that's a typo there again. Our formula is, what's that? There it is. So our formula is our open circuit voltage, not our open circuit current. We don't have open circuit current. We don't need it. Our formula is internal resistance equals our open circuit voltage minus our closed circuit voltage divided by our closed circuit current. And what that looks like is our open circuit voltage, 12.6 volts, minus our closed circuit voltage, 12 volts, divided by our closed circuit current, 6 amps. And that is going to equal 0.1 ohms. And that is the internal resistance of that battery in that example. Moving on to life cycle of a lead acid battery. The number of complete charge over discharge cycles a battery can perform before its normal charge capacity falls below 80% of its initial rated capacity. So the number of times that a battery is charged and discharged in a cycle and can perform at its normal capacity is the life cycle of a lead acid battery. Once it starts falling below 80% of its initial rated capacity, the battery is not operating at a performance rate that that meets the standards for aviation. Factors that affect battery life cycle. There are various factors that can cause deterioration of a battery and shorten its service life. 1, sulfation. Okay, so I'm sure we've all seen this before. Where'd my mouse go? Being mechanics, we have this sulfation right here. This is our sulfuric acid bubbling up and collecting around our terminal. And remember, it has a very high resistance to current flow. Sulfation is a result of the electrolyte fluid level in the wet cells falling below the top of the lead plates and exposing them. Sulfation is caused by over discharging. This can cause excessive sulfation. And another image of some sulfation inside the battery cells and on the plates. 2. Too rapid charging or discharging that results in overheating of the plates and shedding of active material. Shedding. What's shedding? Shedding can be described as corrosion that occurs primarily on the grid in the battery, and it is known as a softening and shedding of the lead off the plates. This reaction cannot be avoided because the electrodes in a lead-acid environment are always reactive. Lead shedding is a natural phenomenon. It can be reduced but not eliminated, but we definitely want to keep it reduced. If we are too rapidly charging and discharging our batteries, then it's going to cause excessive shedding. 3. The accumulation of shed material causes shorting of the plates and results in internal discharge. 4. A battery that remains in a low or discharged condition for a long period of time may be permanently damaged. And I think that's it for today on lead-acid batteries. So don't forget to take the quiz tonight by midnight. Review this material because the questions will be specific to the lead-acid battery lecture today. Any questions? I don't know if there's anybody else in here, but if there's not any questions, feel free to go ahead and leave lecture. The slides will be available tomorrow. The quiz tonight will be available at 6 p.m. and you guys will see Mr. Kimball in lab tonight. If you have any questions, go ahead and type in the chat. If you do not, then I will see you for lecture on Wednesday. We'll be going over NiCad batteries. Yes, I see you have a question about the midterm. If you guys do have questions about the midterm, feel free to ask me now or email me. I believe that the correct answers are up on the midterm, but if you have questions or things that you would like reviewed, you can email me and I will answer those and or post those on Canvas so that everyone can see those. I have taken a look at the midterm. I will go through it and see what questions were missed the most and probably post reviews for those on Canvas. I have not done that yet, so I will do that between now and Wednesday. But if you have questions about the midterm, you can ask them now and type them in the chat. Or you can email me if you don't want to ask me in the